Thank you very much for joining for taking part to another session of our Game on Seminar series. It's a great pleasure for us to have Scott Guan joining us today. Scott is a postdoctoral fellow at Georgia Tech, and he works on multi-agent systems, on learning, on especially for systems with a very large number of agents. So I see that your work has been mostly on the intersection between learning, games, mean-field games, and trying to developing very scalable algorithms that work in very large population of games. So I think that your theme really resonates with the themes of our seminar series, and I'm very glad to have you here. Please, you're very welcome to take the floor.
Sounds good. Thank you so much for having me today. So again, I'm Scott Guan from Georgia Tech. Today I want to talk about our recent work on learning large population competitive behaviors using some mean-field approximation approaches. So without further ado, let me start with this little video of birds flocking around. I think no one can say that this is boring. Well, maybe people think it's boring, but to me it's very intriguing, and especially let's say large population type of intelligence, and then to some extent I think it's very beautiful. And then when I was younger, when I was in my hometown back in China, I normally look at these kind of birds flocking over a lake called West Lake. It's a very famous place. And then that's also maybe that's where my journey with game theory, large population games started when I was a kid. But yeah, so I just want to plant this little seed in your head for large population intelligence. All right, so a quick motivation of why we care about multi-agent system or even large population system, because I think multi-agent system are and they will be pretty much everywhere. So we have already seen them in warehouse automation, agricultural, transportation, and I think in the very near future we're also going to see them in space exploration. So I think it's a very interesting and also exciting area to work on. So for multi-agent systems, normally we have this perception, decision, action loop, meaning that you the agents need to understand how the environment is, and then based on that, they are going to make a decision of how they are going to interact in the environment, or how they are going to react to different kind of stimulus. And then in the end, they are going to use some kind of actuator to actually make action and then influence their state or how the environment is evolving. So there are people working on different kind of aspects in this loop, but for me, I mainly work on decisions. So I think a lot of challenge in nowadays multi-agent system application comes from the growing complexity. So I regard that in two different kind of orthogonal axes. The first one is we're working with more and more complex environment. So this is, I think, maybe 10, 15 years ago when I was in junior high school, we were working with a robot navigating in a maze. But now we have, this DARPA challenge that you are asking a robot to actually navigate through tens of kilometers in a desert. So the environment is obviously much more complex. And then at the same time, the task that we want these robotic systems to accomplish gets more and more complicated. That requires a large number of agents to work together to actually accomplish. So this corresponds to this larger team size of growing complexity. So for my PhD work and also my current research, I have work on both of these axes. But today, obviously, as the title suggests, I'm going to mainly focus on this larger team size challenge. All right, so let's ground this decision-making problem in a more formal and mathematical way. So we are going to formulate this under a Markov decision process framework for a single agent scenario, where you have a robot that is interacting with the environment through some kind of action. So this action is going to influence how the state of the environment is going to evolve. And then in return, the robot is going to get a reward and also an observation from the environment. So the objective for the robot is to develop this decision rule that tells you, given an observation, what kind of action you are supposed to select in order to maximize the reward that it is going to receive. So single agent problem, things are pretty much well studied to some extent. But then things gets a lot more interesting when you have multiple robots interacting with the environment. Now the environment state is evolving, is controlled not only by you, but also by your peers or maybe even your adversaries or your opponents. And then your reward also not only depends on your own state and your own action, it also depends on other robots' action and state. So that gives you a coupled optimization problem. And then to fully understand how you're going to optimize, you also have to put yourself in the shoes of other robots in order to understand how they are going to behave in the future. So this problem is significantly more complex than a single agent problem. And then I call it a fundamental challenge for the multi-agent system. So let's put it, the multi-agent system in a more concrete and mathematical way. So the framework that we're going to use is this thing called stochastic game, where you have the state action spaces of agent I denoted as xi ui. And then you also have the reward for agent I that depends on the joint state and action of all agents. And then you have the transition kernel for the joint state that tells you if all the agents are at this very specific state, and then they're applying very specific pair joint action. What's the probability of transition to the next state? And then we are considering finite horizon problem. So I will mainly use this scenario as a concrete example throughout this talk. This is a battlefield scenario where you have a blue team of agents trying to defend a target, and then the red team trying to breach the defense and then attack the target. So that's the scenario that we're going to talk about mostly. And then obviously this can be put into a stochastic game framework. And then observation is a mapping from the joint state and joint action into some kind of observation. For example, here, if you have local observation of the agents around you, then this is what you see. Everything else, you just doesn't observe. And then the strategy here is mapping from your observation to an action, basically where you should go next in the scenario. Optimization, every agent try to maximize its cumulative reward. And then the challenge here is that we have n couple of optimizations if you have n agents. And then you may also suffer from complex information structure, meaning that you don't observe everything. And then what you observe may also be different from what other agents are going to observe. So people have shown that for this generic class of stochastic game with complex information structure, it's a very hard problem to solve. It's actually NEXP. It's actually harder than MP. So with that being said, obviously we're not going to solve the generic version of the problem. We have to impose some additional structure to the problem so that we can achieve our scalability. That's why we propose this class of problem called mean field team game, which is a large population team versus team problem. It's a generalization of a zero-sum two-player game to a team versus team two-team problem. And then this gives us a mixed collaborative competitive setting in the sense that agents are collaborating within the team to achieve a certain team level goal. But at the team level, they are going to compete against each other, like the battlefield scenario I just talked about. So a quick overview of the results that I'm going to cover. So we're going to establish some theoretical results showing that for this class of problem, using identical team strategies is enough. And then we show that we can reduce this n versus n problem into an equivalent two-player game formulation. And then in the end, we show that after doing all these approximations, we're still epsilon optimal in our original setup. And then all the theory is developed to give us insight and also the structure to develop the scalable multi-agent reinforcement learning algorithm that we call MF-MAPPO that are able to actually train and scale to hundreds or thousands of agents. All right, so let me quickly decipher these words. So we have mean field and team games. So let's start with mean field. So the key intuition behind mean field games or this large population approximation is that if you have a large population of homogeneous agents, then you don't really need to track individual agents' whereabouts, or you don't need to track each individual agent's state. You can just approximate the system behavior, or you can model the system behavior by the agent's distribution over the state space. That gives rise to this idea of mean field, which captures the fractions of agents on each state. For example, if you have this 5-state system and then you have 2 agents here, one agent here, one agent here, then the mean field is given by the following, which states that 50% of agent is on this state, 25% on each of these states. All right, so what is the most important thing here, or something that really allows the scalability, or this is the main assumption that we have to make, is what we call a weak coupling. It means that your reward is coupled with other agents, not through joint state, but through the distribution of agents. And then similarly, your transition dynamics is coupled with other agents through the mean field as well. So instead of with the joint state. Obviously, I don't have time to really cover what people do with standard mean field games, but I can give a quick overview of the two main branches in the literature. The first branch is called mean field game, where you have n or a large number of selfish agents, each trying to maximize some cumulative reward on its own. And then you have the mean field control and mean field team game, which is a collaborative scenario where the agents are trying to maximize a team reward together. But the most important thing is that all of these things will resolve a mean field equilibrium. It's an equilibrium concept that only consider a single agent unilateral deviation, meaning that you have this n agent population. In the end, you want to find an equilibrium so that everyone is optimal. And then if a single agent deviates from the optimal strategy, then you cannot gain anything, or you can only gain epsilon performance. So I'm listing out this thing here because I want to show that we're going to generalize this. So remember, single agent unilateral deviation. All right, now we can move to the team game part. So the team game is a mixed collaborative and competitive setting in the sense that at the team level, the two teams are competing against each other, but within the team, the agents are collaborating. I've already talked about the battlefield scenario, so I hope this is clear. And then in the battlefield scenario, let me just reinforce this idea of mean field. If we apply the mean field approximation, then instead of tracking all these agents, you're here, you're here, you're here, we are just saying that, okay, the population is modeled by the distribution of agents over the grid or over the battlefield. Now the team game is formulated as this max-min optimization where each team is maximizing, the blue team is maximizing the performance using its team strategy, and then the red team is minimizing this performance using its team strategy. So if you have N1 agents and you have N1 strategies that you want to optimize simultaneously. The key challenge here is that now, because we have a team game, we need to consider team level deviation instead of just a single red agent deviating from its policy. So this is slightly more challenging than the standard mean field analysis. And then at the same time, the most important thing is the non-identical team strategy, meaning that every different agents technically should be able to apply different strategies, even if they're within the team. So I'm going to talk a little bit more about it later. But in the end, the bottom line here is that now you're reasoning with this joint policy space or strategy space, so your complexity scales exponentially with the number of agents. So the more number of agents you are going to reason with, the more challenging the problem becomes. And then essentially it becomes intractable once you hit, hundreds of agents. All right, just a quick recap of mean field team games. We're considering a zero-sum simultaneous move game with two teams. Each consists of n homogeneous agents and could be very large, for example, like hundreds, even thousands of agents. We're considering finite state and action spaces. We have finite horizon. And then in the end, the most important feature of mean field team game is this weak coupling through the state distribution on the mean field, where your dynamics is coupled with other agents through the distribution of agents as well as your reward. Okay, so the very last structure that we're going to put on this problem, and also I think it's kind of standard, is what we call the mean field sharing information structure. So this is the class of strategies that we're looking for. So for the blue agent, it is going to observe the distribution of both teams over the battlefield, and the plus is going to use its own state to select its action. So this is the strategy class that we're looking at. Grounding it back to the battlefield scenario, this is when the agent is going to look at its position in the battlefield, the distribution of both teams in the battlefield, and then based on these information, it's going to select an action. So the most important thing here is that the mean fields of both teams or the distribution of both teams are commonly available to all agents. This is a structure that we're going to exploit to achieve scalability later on. Again, the optimization objective here is this max-min optimization. And then let me reiterate the key challenge here. So here, at this optimization, at this point, we're allowing different agents to apply different strategy, especially the opponents. Because in a lot of the mean field literature or large population literature, people like to assume that every agent is going to apply the identical strategy. But this is not a good idea where you have a competitive team scenario. Because if you're controlling your team, you can safely say that, okay, all of the agents go ahead, apply this identical strategy. But then if you are facing an opponent and then you assume your opponent is applying identical strategy, you are significantly underestimating your opponent's capability and also their flexibility. So you better justify and then prove that it is an acceptable approximation. Otherwise, your performance can be very bad. So this is one of the key challenges that we will address next. All right, with that being said, we are solving this optimization problem that allows different agents to apply different strategies. The very natural question we want to ask is that, can we still approximate in this zero-sum team game scenario using identical team strategy? And then how bad are these identical team strategies? This is shown by our approximation lemma here that basically states that if you're given an identical team strategy, and then you induced some kind of distribution at the next time step, then there always exists an identical strategy that gives you almost the same distribution at the next time step. And then this error of this approximation is bounded by this 1 over square root of n rate, meaning that the larger the population is, the less this approximation error is. So the key takeaway here is that the set of identical team strategy is actually rich enough to approximate team distributions induced by non-identical team strategies when the team size is large. So I think this also matches with our intuition here. So this leads to the idea of solving this n versus n problem at the infinite population limit using identical strategies. So that when we're solving the game, we don't suffer from any kind of approximation error when we're using identical strategies. Now, we will further exploit this information structure to reduce the problem. So right now, the information structure states the following. The agents are acting based on its local state information plus the mean fields, or this commonly available information to select its action through this identical strategy feed. So this actually allows a two-phase decomposition of the decision-making problem. First, we only need to process the common information that is available to all the agents using a coordination strategy, alpha T. So this alpha T is going to observe the mean field and then select a local feedback strategy, pi T. And then what happens next is that each individual agent is going to look at its own local state, plug that into the pi T, and then it's going to select an action based on that. So instead of directly mapping from the local state plus the mean fields to the action, we factor this decision into a coordination plus a local execution scheme. And then we can show that there is a one-to-one correspondence between your coordination strategy and the original blue team identical strategy. And then the most important thing is that the key enabler here is that identical team strategy structure, because otherwise, the coordination strategy need to assign different local policies to different agents, and then that just breaks all the scalability thing that we're going to achieve. All right, so with that decomposition, what we can do is that we can decompose this n versus n problem, solve it at the infinite population limit, and then approximate it using an equivalent zero-sum game between two fictitious coordinators. So the coordinators is going to observe the mean field. Based on the mean field, it's going to assign this local policies, local feedback policy, and then each individual agent is going to look at its own state, plug that into the local feedback, and then select an action. And then we can regard these local feedback policy as the actions of the coordinator. And then the state of the coordinator is essentially just the mean fields. And then we can show that this problem now is reduced to a two-player zero-sum game and can be solved via a dynamic program approach. Okay, so here's the final main theorem So if you recall, there are three major approximations that we made. First, we approximate this problem with identical strategy. Second, we solve the problem at infinite population limit. Third, we reduce this problem into a equivalent zero-sum game between the two fictitious coordinator. So that's a lot of approximation. And then in the end, we obtain this identical coordinator strategy that corresponds to a very specific identical team strategy. So the question is, how good is this team strategy after doing all these approximations? So what we can show is that if we deploy this obtained strategy in the finite population game, and then we allow our opponent team, in this case, the red team, use non-identical team strategy to exploit your strategy, what you have achieved is still epsilonly optimal compared with the original, compared with the performance that you could have achieved if you directly solved the original M versus M problem to the true optimal. So I think this is a very cool and strong result. The key takeaway here is that if you are solving this class of mean field team games, you can consider only identical team strategy, and then that's enough if your population size is obviously large enough. Yeah, so that's the key takeaway. And then we're going to validate it first in a tiny little two-state, two-action space example. I'm not really going to talk about the detailed setup, but the idea here is that this thing is engineered, this example is engineered to validate our solution so that we can show that the optimal blue team strategy is to match a distribution of 1 over square root of 2, 1 minus 1 over square root of 2 over its two states. Why we designed this is because this is feasible only at the infinite population limit, but not with any finite population, because this is a irrational number or irrational distribution. And then we can also show that for finite population blue team optimal strategy, it needs to be non-identical. So this thing is engineered so that we have this set up and then test our theoretical guarantees. So what we have achieved is that we solve this thing using a discretization and also a dynamic program. And then we do see the value function peaked at this 1 over square root of 2 distribution. So that's good. We know that we are matching the optimal. And then we can also compute exploitability because we have the analytical solution for the blue optimal strategy. And then indeed, the exploitability is bounded by the predicted order of 1 over square root of n by the theory.
Sorry, can you
Yes.
just clarify what is in the axis on the left plot?
Oh yeah. So the axis, because you only have two states, right? So you can characterize the distribution of the population using just the distribution on that very specific state, right? Because the other guy is just 1 minus that. And then this is the distribution of the blue team. This is the distribution of the red team. Yeah. So the key thing to illustrate is that it indeed achieves a predicted optimal solution. That's the most important thing here. All right.
Thank you.
Yeah. Thanks. Okay. Now the thing here is that we don't want to stop with just this two-state, two-action little example. We want to deploy it to some more realistic large-scale scenarios, right? Like the battlefield that we just talked about. So we're going to develop some multi-agent reinforcement learning algorithm. So what happened here is that we're going to leverage, so most of the modern day multi-agent reinforcement learning algorithm or MARL algorithms relies on the centralized training, decentralized execution scheme, which I'll just call it CTDE. What happened here is that during the training, you are going to put pretty much all the available information into the critique so that the critique can evaluate very efficiently and also very accurately the current situation and the future performance of your agent. But the problem here is that you have to put a lot of information into the critique, and then sometimes that overwhelms the critique. Yeah, so most cases, if you just naively apply the centralized training scenario, then you put all agents' observation into the critique. And then if you have hundreds of agents, and then if you just naively apply that, you're going to put a lot of information into the critique, and then the critique probably just won't be able to train because it's just too much. And then at the same time, for the decentralized execution part, individual agents need to have individual actors. meaning that different agent, because different agent technically will have different strategies, right? So if you have 100 agent, then you end up with 100 actors. There are techniques that you can play with. Maybe you can do parameter sharing in a neural network so that you help a little bit with the scalability issue with the number of agents, but in general, it's a challenge. So what we can do with our theory that we developed for all of these mean field games is to use that and then build a scalable multi-agent learning algorithms that we would call MF-MAPPO. So we'll rely on two major insights that we obtain from the mean field team games. First, the value of the mean field team game only depends on the mean field. It doesn't depend on your local state. Second, we show that we only need to use identical team strategy. Based on that, we're going to design this MF-MAPPO. So I will quickly go over the two modules or the two key features of MF-MAPPO. The first one is what we call a minimally informed critique. It's a PPO value-based critique, standard to most multi-agent learning algorithm. But we only use the mean fields as input instead of having different agents' observations as input as well. And then because we are only using the distribution over these grid as input, the complexity or the dimension of the input does not scale with the number of agents because no matter whether you have just 100 agent or a million agent, in the end, you end up with a distribution over the battlefield. So that's the minimally informed critique. And then we're going to explore this identical team policy result by just implementing a sheer team actor for the entire team. So the blue team, instead of having n different actors, we're only going to have a single blue team actor that is shared by all the agents. And then during the centralized training phase, we're going to feed all agents local observation in parallel into the team actor, and then train it. And then we will also simultaneously train the blue team actor as well as the red team actor. And then during decentralized execution, each individual agent get a copy of this actor, and then they deploy it using its local state and also the mean field that it is going to observe, and then select their actions. All right, so that's the MF-MAPPO algorithm, and then we were going to validate it first with a rock, paper, scissors scenario. So it's an extension of the standard rock, paper, scissors to a population game. So each individual agent has three different states: rock, paper, scissors, and then we make the game a little bit more challenging by adding dynamics to it so that you can only move from scissor to rock, but not from rock to scissor. So it's a counterclockwise movement here. So that's why we call it a constrained rock, paper, scissor. And then the reward in the end depends on the population of the blue team and also the red team. And then the payoff matrix is the standard rock, paper, scissor payoff matrix. So all these setup is to make sure that we have an analytical solution that we can try to match before we dive into the battlefield scenario where things get too complicated and then there's no way we know the true optimal solution. So the equilibrium solution in this case, as everyone would expect, is a uniform distribution over all these three states. And then we train our algorithm. We can show that indeed the MF-MAPPO actually converges to this equilibrium distribution. And then there is another algorithm developed called DDPG-MFTG that fails to converge, which is good for us. But the reason why the DDPG, roughly speaking, the reason why DDPG-based approach failed to converge is because they are using deterministic policies. This is roughly speaking. There's a lot of technical details here. But the key idea here is that because MF-MAPPO allows mixed team strategies, and then we allow agents to randomize at each state, this is part of the reason why we are able to converge to this uniform distribution over the state. Okay, now we can get to the battlefield scenario that I've been talking about. So we consider this battlefield scenario. Let me just quickly reiterate what is going on here. The first thing here is that the blue team is trying to attack or reach the target, and then red team tries to defend or try to eliminate the blue team before it reaches the target. And then to make we add an additional layer of complexity of this activation deactivation mechanism, meaning that if you are in a cell and then your team, for example, if you're the blue team, your team gets overwhelmed by your opponent in number, in this case, the red team, then you are going to get probabilistically eliminated or deactivated with the deactivation rate proportional to this numerical advantage or the numerical disadvantage that you're facing against your opponent. Yeah, so in this case, the teams or the agents needs to learn not only just how to attack, defend, how to reach the target, avoid the other agents. You also need to learn how to avoid getting deactivated by the other team. So it's a relatively complex scenario, and then we're working with hundreds of agents here. All right, so let me show you two simulations or two behaviors that we observed. The first one here, you will see the blue team learns to fake an attack or fake an attack to the target one here, and then it will switch its attack. So this is an interesting result, and then you can see some of the agents get deactivated while they are moving, and then the red team, the most important thing is that the red team is doing the logical stuff of blocking these corridors, but in the end the blue team actually enters the target too. In the second scenario, you will see that the red team learns to block both corridors, and then we will take a closer look later on, but let me play the video first. And then a small fraction of the blue team actually gets deactivated here. So if we take a closer look at what's happening here, is that at the very beginning of the game, there are 4 sub-team of blue agents, and then they are moving towards the closest target, right? And then the red team started as a single blob. It actually splits its population into 2 different groups, one aiming to block this upper corridor, one aiming to block this bottom corridor, which we have already observed. And then the interesting thing here is that the breaking of the population is actually proportional to the size of these blue team that is seen here. So some of this red team has more agents in it. This red sub-team has a smaller number of agents. And then what happened here is that this red team was actually able to get into position sooner than the other agents. So this blue team actually realized that, okay, the corridor has already been blocked. It's better to shift its target towards the bottom one. And then after observing that, the red team actually breaks some part of its population to help reinforce this corridor blockage here. That's what we see here as they are moving around. And then in the end, they get reinforced, this bottom corridor, and then the blue team gets eliminated there. So these simulations, I think, really give us this key takeaway here is that, first of all, we need to use mixed team policy to ensure convergence. That has been demonstrated with the rock, paper, scissors scenario. And then the more important thing is that the mixed identical team strategy is actually capable of generating heterogeneous behaviors. By saying heterogeneous behavior, I mean the red team actually have different roles, right? So some of them decided to block the upper corridor, some of them blocking the bottom corridor, and then you even can see that they form a task force to reinforce. So it's a relatively complex scenario. Or a behavior. And then at the same time, I also want to emphasize that we train this algorithm without any reward engineering. So the reward is very simple. We just set the reward to be the number of blue agents in the target. That's it. We don't do any kind of engineering there. And then all the behavior are emergent from the MF-MAPPO and also this mixed team strategy. So why I really want to mention that is that when I first talk to other people about using identical team strategy, one criticism or one skepticism is that you're using identical team strategy. What we are expecting is just this red team moving in a single blob, and then it's just boring scenario. There will not be any kind of heterogeneous behavior. But in the end, by using mixed identical team strategies, you are still able to generate these relatively complex and heterogeneous behavior, which I think is pretty cool. All right, so that's pretty much the end of my talk. So a quick summary of what we have done. So we introduced this new class of zero-sum infield team game, which is a collaborative competitive scenario. And then we show that under this mean field assumption plus some common information structure, you can actually solve the game using just identical team strategy. And then based on all the mean field theory and the performance guarantee that we developed, we built this MF-MAPPO algorithm that has this minimally informed critique. It has a shear team actor so that each team only has a single actor. And then in the end, we achieve this tractable learning for large population teams. In the battlefield scenario, I think we're running maybe around 200 agents. So I think maybe people will ask me what are the limitations, right? So obviously we assume that both teams are observing, or all the agents are observing the mean fields or the distribution of both teams, which may not be very realistic. So we also have some follow-up work on, using consensus-based algorithm to estimate the mean field distribution. There are also work on trying to use some kind of locality to directly derive a local feedback policy for that. And then another promising direction I think I would be very interested in is using to address this heterogeneous agents and also subteam roles and behaviors. For example, maybe some of the red agents or some of the blue agents have better mobility or better firepower or whatever you want to call it. And then with that heterogeneity added into the system, how the system is supposed to behave. So with that being said, I would like to thank my collaborators and also my sponsors. And I'm ready for any questions. And I just want to play this video again because it's really mesmerizing. Thank you, everyone.
Fantastic. Thank you so much, Scott. I see Giuseppe clapping, and we have the usual bug that the clapping is actually canceled by Zoom. I see a couple of questions. I think that the first one to ask was Ezat, who wrote in the chat. Ezat, feel free to unmute yourself and ask directly. Still there, Ezat? Okay.
Yes,
While we wait for...
sorry,
Oh, yeah.
I'm here. Sorry, my Zoom froze right when when it was time to ask. Thank you, Scott, for the nice talk. My question is, okay, so you mentioned that the usual mean field games make an assumption that all the agents follow the identical strategies.
Yes.
But there are formulations that consider subgroups of agents or types.
Right.
So how is that different? And essentially you can view different types of agents as an additional state that is static, and everything goes through from there. So how is that different, and what is the key role of the zero sum and team structure that makes it different from an MFG with different types?
Right. So I think that's a great question. So I think by having this fully competitive scenario, you have a structure that is completely different from the standard mean field formulation in terms of this adversarial team setup, right? So let me try to rephrase myself. So first of all, we have to consider this team level deviation. I think that's not a problem, right? Because you have to assume that your opponent may behave completely differently than what you expect, right? With that being said, in this case, you just cannot consider a single agent deviation. And then most of the mean field result established on this single agent deviation, because you have millions of agents, you only consider a single agent deviating, then the single agent deviation doesn't cause any difference to the population evolution, right? But now if you consider a team level deviation, then the evolution of the mean field trajectory will be completely different, and then you have to react to that. So I think that's the key structure that makes this problem different. from the standard multi-population or subpopulation setup or different types of agents set up in the existing mean field literature. Does that answer your question?
Very clear, yes. And
Great,
and then
thanks.
so far you can only tackle this then in zero-sum structure,
Well, I
or is there
mean,
hope to generalize?
yeah, I think generalizing to general sum is just swapping the operator of zero sum min max optimization to a general sum Nash operator. I think that's straightforward. But just for me, I like to work on things that are the first step, and then to pick simple things as the first step. So that's why I picked zero sum. And then actually for the MF-MAPPO algorithm, if you don't care about any kind of theoretical guarantee, you can just borrow our code and then implement it for a general sum scenario. Yeah.
Yeah, okay. So probably the crucial point of the zero sum is to guarantee convergence. I think that's where things tend to break.
Yeah.
But your other approximation results probably might hold beyond.
Yes.
Okay.
Right. I think that there was another question from Giuseppe. Is that right?
Yeah, I had a question. Hi, Scott. Thanks for the great talk. I have to say I'm also quite mesmerized by this block changing
Oh, yeah.
shape in front of the slides. Fantastic.
Yeah.
This is what usually robotics people do in their slides to keep the audience engaged. Anyways, my question is about the computational tractability. I was wondering how far can you push it in terms of population size, if that even matters?
There is no limit on the population size. So the policy that you derived in the end, let me try to get it. If you look at this policy, right? So the input depends on your own state and the distribution of the population. So it scales to an arbitrary number of agents. Even if you give me a million number of agents, right? I mean, in the end, it's just this distribution over, in this case, a 5x5 grid. You just plug it into the network, and then you plug in your own state, you get an action directly out of it. So there's no number of agents issue. Well, but then technically we train this MF-MAPPO in a finite population simulator. But if you want to train it with a million agents, then the burden actually lies upon the simulator, not really on the algorithm per se.
I understand. Very clear. Thank you.
All right. I will
Thanks.
take a question myself, actually. Yeah, we still
Okay.
have a bit of time. So when you presented the main theorem on the approximation power of the mean field approach, what are the key assumptions here? Can you always say that the infinite population result approximates a finite population optimal strategy?
Okay, so let me make clear about assumptions versus simplifications, right? These are two different things, right? Assumptions are what we made, and then I don't even try to prove that, okay, whether these assumptions make sense or not. But simplifications or approximations are something that I made, and then in the end, through the theorem, I will show that this approximation works for the original problem. So assumptions are the ones that are in the problem formulation, and then I just regard that as take that for granted, and then the approximation part I try to prove. So the key assumptions, the assumptions that is intrinsic to the problems are the weak coupling, meaning that your reward and dynamics are coupled not through the joint state, but through the mean field. That's one assumption. In addition to that, we assume some Lipschitz continuity in the reward and dynamics. I think that's reasonable as well, because without Lipschitz continuity, you cannot prove anything. And then the very last assumption that we made is this mean field sharing information structure, meaning that every agent observes the mean field plus its own local state to take an action. So these are the assumptions, or you can call it the key features of the problems that enables this mean theorem. But what this mean theorem actually states is that if we take these assumptions of the problem or the features of the problem as granted, then what we did is the following three approximations. The first one is the identical team strategy. The second one is the solving at infinite population limit. The third one is the coordinator game. And then after doing these approximation, I can show that these approximation doesn't really change the optimal behavior of the population that much, or the optimal performance that much. Does that make sense to you?
Yeah. So actually, yeah, the assumptions are way weaker than I
Yeah.
had in my head.
So
I guess actually quite reasonable.
Yeah, the end result is I compared it with the most generic n versus n optimal solution. So if you directly solve the problem using whatever the strategy, whatever the solver you have, to the true optimal n versus n optimal solution, then it's actually still very close to what I can achieve with my approximated solution that I obtained through the 3 approximations that I just talked about. Yeah.
And I have another question. On a couple slides later, you showed my iPad just died. A couple of slides later, you showed an example with only 2 states and the population,
Yeah.
like exactly. So here, it is not really clear to me when you say that the finite population is non-identical, yet you managed to approximate it with a team identical strategy. Is that correct? It feels like a discrepancy here.
Okay. So if you directly solve the n versus n problem, the true optimal will be non-identical team strategy. I think that's as expected, right? Because sometimes, for example, 3 of us, we try to achieve a distribution. So, suppose you are 2 agents here, right, on state 1, and then you want to achieve a distribution of 1 agent here, 1 agent here. If you want to achieve that distribution, the true optimal way to do that is a non-identical strategy tells agent 1 to move to the other state while agent 2 stay, right? But at an infinite population limit, if you want to achieve one half, what you can do is that you tell 1/2 of the agent, you use an identical strategy such that the agents are randomizing 50-50, 50% of time, 50% of the time they go to X2, 50% of time they stay. And then when you're at the infinite population limit, that's exactly the distribution that you will achieve. But if you only have 2 agents, then sometimes both of them go to X2, sometimes both of them stay in X1. And then that's when you start to have this performance degradation. Does that make sense now?
Absolutely.
And then
Thank you so much.
in the end, we're just comparing the performance. We're not talking about just approximated strategy. I'm talking about I have a identical team strategy that will achieve almost the same performance.
Yeah, for a very large population.
Yeah.
That's very clear. Okay, I don't have personally any more questions. So is there any more question in the audience? I don't see any in the chat. Let me double check the Q&A here. But yeah, I don't see any. If not, 3, 2, 1. Okay, no more questions. We're done. Scott, thank you so much for participating and for contributing to the seminar series. Thank you everyone for participating. And we'll keep in touch and we'll see you all next week.
All right, sounds good. Thank you so much for having me. Thanks.